very excited to be here. Thank you all for coming. So my name is Hadar Isserlis. I'm an electronics engineer. Ever since I remember myself, I was building robots. Started as a kid with lots of Lego, Technic Lego. Later on, I took apart an old keyboard, connecting it to a rotary switch. I made it my first wheel encoder, reading the inputs with a simple Pascal code. Very a great moment for me. Something about a decade later, I found out the world of Arduino, which made a great connection for me between the electronics world and the software world. And a little bit later, the world of multirotors. Ever since I'm building ones, first flying them manually, today also autonomously. This is actually one of my first quadcopters. Flies very well, as you can see, made of some wood sticks and etc. If you recognize, there's a pointer here also. Oh, okay. This is an Arduino. We have IMU here, digital compass, barometer. We'll talk about it later. So a little bit about the history of multirotors. I found out it actually started in 1907 by French brothers that, as you can see, made this vehicle. They managed to take off and to land, and they said the flight is too shaky and not stable, so they neglected the idea. Almost 2 decades later, you can see another French engineer took off and made a flight of 360 meters. Very impressive. Jumping to today's technology, first manned flight. And this is today Evolo, Volocopter, or something like that. And as you all know today, drone serves us in many, many fields. Delivery, photography, military, and art, and also sport and racing. Israel is really a leading country in this field. We have a lot of startups and companies. If I'm not mistaken, Robotics were the first one to get licensed to fly autonomously in Israel, maybe also abroad. So if you're here for this, you're in the real field. Okay, so let's build a drone. So first of all, I want to show you a typical quadcopter setup. This is very old, but it's a typical setup. And it is built of 4 main components. So it has an energy source, battery. It has something that drives it. It has a processing unit that we'll talk about all later in details. And we have a device that gives the processing unit the commands what to do. Of course, on this other side, there's a man with a remote control. So taking one step back, I would like to understand first what do I demand from this multirotor, multicopter, multirotor drones. So first our task obviously is to take off, hover and land, and this is how it's done, and we'll talk about it. I'm not just showing it to you here, but we'll talk about it in terms of when we are planning. He told me to drink water. No, just kidding. We'll talk about it in terms of planning our setup. This is very important. Moving forward, we also like the quadrotor to move in space, right, left, forward, backwards, which are, of course, the pitch and roll commands and also turn in place, yaw. Okay, so of course throttle, up, down, roll, pitch, and yaw. Unlike, if you don't know, unlike regular helicopter, normal helicopter has one big rotor and one small one that is in 90 degrees that allows, first of all, cancels the rotational by the big one, and also helps it to rotate. Here in multi-rotors, we use different rotation direction to do that as part of the setup. Moving another step back, this is here, you all know 3 laws of motion from Newton. I only want to translate it for us to our world. So the first one simply says, okay, you managed to take off, you gave it a little bit of pitch or roll, but if you leave the stick and it already has velocity to some direction, if you don't stop it, it will continue. This is something that we must remember. Unlike a landed robot with a gear that will probably stop once you stop the command, here the drone will drift somewhere. We need to take that in account when we build an autonomous drone. The second one we saw earlier, and the third one basically says when you hit a wall, and you will hit a wall and ground, the wall hits you back, so buy spare parts and etc. We'll talk about it. So one of the first steps to when we plan our quadrocopter or multi-rotor is selecting the configuration, and we have several parameters to take here in account. First one is the payload, and if we know the payload we would like to take, we can, I will show you later on how to calculate it by looking at specs and of motors, but for now, just like a rule of thumb, we can assume that more rotors will give us more thrust, right? But on the other hand, they will add us some weight and maybe make the multi-rotor larger. A good part of it is a redundancy part. So if you have this drone, unless you are developing algorithms in MIT for flying multi-rotors with one or two rotors, this one will probably crash. Also this one. But this one, those two, even this one and this one, will manage to continue flying if they have a motor failure, sometimes even more than one motor. Next step will be to actually select our frame, and here we have also several parameters to take in account. The cost, of course, the budget, the robustness of the setup. So again, we must take in account that we will crash our multi-rotors during our tests, development, and we will also like to take in account the maintenance thing. We are developers, so we would probably want to take it apart, add components, remove components, connect again, leave room for electronics, more electronics, sensors later on when we'll make it autonomous. And also here, efficiency and noise. Again, a rule of thumb: as long as bigger drones, bigger rotors, propellers means less RPM, less noise, more efficient. Something we can take in account. Okay, so next step will be choosing our motors. So we have, generally we have two types of motors. We have brushed motors and brushless motors. The brush motors are generally used in these small ones, small toys, or also not toys, but the small copters. They are less efficient. They are lighter a little bit. Their driving is a little bit different. I will show you later. And brushless is the opposite. Looking at motor spec, and this is where things start to combine. This is actually a spec from a manufacturer of a motor. This is another motor. We have a lot of information here, and it's a good start. The manufacturer tells us my motor is working at 11 volts, and I'll show you later what it means in terms of battery selection. And you can put, if you want, an 8-inch propeller or a 10-inch propeller with a pitch of 4.5. And if you do that, you will get a thrust from one motor with this, for example, a propeller. You will get a thrust of 490 grams. So if you're building a quadcopter, we have 4 of these, so we already can know that we can lift, or the total payload can be almost 2 kilos, sorry. This is actually amazing, but we don't want to take the 100%. We should aim to the area of 50%. So I will explain in terms of control and the PID later. So this is a start. And if you have this information, you also know the size of your copters, right? It's simple geometry, 8-inch, 4 of these, 6 of these, and it's sort of the chicken and the egg dilemma. You need to do several iterations to understand the total payload, and then the size, and how I showed you here. So if you selected your motor, it will be a very easy task to choose the driver. So this is a simple driver for a brushed motor. This is a driver for a brushless motor, and you need to take in account 2 numbers here. One is the total amps that it can drive, and the second is the voltage. It's written here in terms of cells, how many cells of the battery in serial, and I'll show you in a minute what it means. So this driver supports 2 to 6 cells and can give you a continuous current of 30 amps. Going back, just to close the entire setup, by this spec, we know how much, if I look at this, the current column, I know how much current I will draw in about 50% of the spec. So we are okay with it in terms of driving. Let's go. So again, you need to choose the propellers. More blades means the motor will work harder, more current. You need to take that in account. I would not spend too much time on this one, but take a look at the spec from the manufacturer and build accordingly. But generally speaking, we have several materials. Again, we have carbon fibers blades, for example, that cost more. We have setups to assemble more easily the props and take it off, take it in account. Again, larger props means more efficient, less noise. Okay, and battery. So battery is a very important part in the setup. If you're new in this field, I would tell you immediately go for LiPo. You also have this one, maybe other technologies I'm not aware of. But basically, LiPo technology for batteries means drawing a lot of current with maintaining the voltage of the battery, which is something that you cannot do with regular batteries in the currents we are talking about. And so you have number of cells here. Let's take a look at that. So this is a 3-cell battery. It says on the battery. The voltage is 11.1, so that takes us back to the manufacturer spec we saw earlier. We have, it tells us how much current, how much discharge rate we can take. And the main thing we need to take from this slide is these two equations. So we saw earlier how much current we will need. So in this term, if we take this battery, we are okay. And we can assume and calculate approximately the flight time we have. This is, of course, for hover. If you maneuver a little bit, you spend a little bit more.
This is not the battery that we use in the step one. It's like light CO4?
It's a lithium polymer. Maybe the one that blew up from LG was something similar to that, but yeah. It's. I will talk about it. This is a battery that you need to keep the charging and discharging. Use a proper charger and discharge, and when you storage it, you need to use a special case in case it taking fire. For that, I have this video showing you they're doing nothing, right? And the battery just, something happened there. Because of the high current the battery can give you, this is very dangerous, and you need to take care of that. Okay, something to take into consider. Okay, flight controller. This is the processing unit, and today there are so many types for different causes, for the targets. For now, I'll tell you, if you're aiming to build an autonomous drone, I would recommend going for a PICSOC, a PX4. It's the same hardware, different stack. So, they support a lot of external components. And inside these flight controllers, there are several sensors. So gyroscope is actually the first and the basic one. And the drone you saw, I built, I showed you earlier, is built only on a gyroscope. It was a nice project that someone took the gyro board out of a Wii console and wrote some code in Arduino. And this is the actual code I put on my open source, of course. This was the first. This is the basic sensor you need. After that, we have a gyroscope measures angular velocity. It means how fast you rotate in each of the axes. Accelerometer gives us the acceleration in each of the axes, And magnetometer is digital compass, of course. Barometer for height, low resolution height.
The gyroscope doesn't give you stability, or it's just a sensor?
What do you mean by stability?
No, because when you use a gyroscope,
So with a simple integration of the gyroscope data in time, you can calculate the angle you're in. The problem here is that you have it's digital and you have drifts. So over time, it will drift. It can be very accurate, but you complete it by using the accelerometer and a filter between them, camel filter or something like that. Okay, we also have GPS, optic flow if you want, range finders, airspeed, airlock. Talk about it. Sorry. So a very important method to do on a quadcopter if you build it yourself is the PID tuning. all of the most of the flight control will come with a custom with already parameters for PID in it, but you will need to tune it according to your setup. Every weight you add or distribute your weight differently, you will need to tune it. Maybe even tune it for the different axes with different PID. I'll talk about it. Some flight controllers has this method built in, which is nice. Sorry? PID is proportional, integral, and derivative. It's a basic controller, loop controller for a closing loop, and in control theory. Look it in Google, you'll see it. We have many GUIs to set up to connect to our flight controllers, to set it up. They also have wizards, so it's quite easy. The most important thing here, and we'll talk about it when we move to autonomous flight, is the MAVLink. MAVLink is a protocol that, for example, ArduPilot uses between the craft and the ground control. It can be either your application, this is actually an application called Tower, or the base station if you use a laptop. Yeah, oh, this is the tower, sorry. Okay, let's take a look at it. Okay. Yeah, so gimbal is a nice accessory. If you're doing photography, if you have a drone with the gimbal, you know what it does. But I'm showing it here in terms of in terms of autonomous setup. This might be useful for us to mount sensors if we'd like, something to take into consideration. Okay, so let's make it autonomous. What do we need? So this is the typical setup we saw earlier. And we didn't see him, but this guy was here all along, flying this setup. And if we are looking at 3 blocks of autonomous architecture, I don't know, this pink, all the setup, all the quadcopter we talked about represents the maneuverability. And the processing unit is doing the basics, today not so basic. You have also GPS and have, you can do a semi-autonomous flight with it, load missions to it. So it's also almost all autonomously, but this guy is representing the perception and the processing if he's flying. So this is what we are missing. So one thing you can do is purchase an off-the-shelf drone with an SDK. This is something we showed in previous meetups. This is something we did in indoor robotics. Gil, Amit. What you see here is what you see here is actually 2 robots controlled simultaneously using a ROS bridge with the SDK of the DJI. This is DJI Mavic. You also have this one. It's also from DJI. It's a brother of this one. It's a Tello Education. EDU. They have SDKs. You can develop with it. Also, you can purchase something like that. Helicopter drone kit, you can buy this kit for something like 500 euros. It already has everything you need, a battery, propellers. They might have made the calculations for you. They also give you a brain to develop on it. The disadvantages in this kind of solution is that you need to use their framework, and you are limited to their setup in terms of sensors, weight, etc., etc. Also here, the Intel Aero. So if you decide to build your own drone and make it autonomously, you need to remember a few things we talked about. Get spare parts, use prop guards, use calculators, online calculators such as eCalc. It's a great calculator for all kinds of, not only multirotors, also rovers and airplanes, flying planes. Tune your PID, perform manual flights. This is something very important before, not only for drones. Any robot you build, very recommended to feel it, drive it yourself, understand the limits and what its capabilities are before you write code to it. Take the orientation of the robot in count. So we have a robot that can be at almost any orientation in space, right? And if I put here, for example, a rangefinder, and I tilt it a little bit to go forward, which I must do, then it points somewhere else. Okay, so we need to take that in account. This is why I put the gimbal. You can take into consideration to use the gimbal. Take in count vibrations. This setup vibrates. It can influence your readings. Dry test it on your table, of course. Distribute your setup for better debugging and have a fail-safe mechanism. This is if you propellers spin very, very fast. Use it safely. Okay, so one thing you can do before even building the drone is using a simulation. If you use ROS, if not, you can start now. ROS is a great platform for developing robots. It's a robot operating system. Gazebo is a simulation platform. What you see here is Hector SLAM package in use. We have a small drone here. If you can see, you managed to see it, right? Before starting to build, this is you can develop your code before even building something or doing. This is a drone using ROS. This is Arvi's visualization tool of ROS. I can see that it has some LiDAR on top of it. As you can see, it moves, rotates, so things to take in count. Thank you.